Where I want to start today is to clean up some of the schedule issues and make sure we're all on the same page. I spent some time the last week or so trying to feel like a human being again, and I think I'm caught up on videos. So looking at these real quick, let's see, Chapter 7, there's a class video, and then there's a video on the t-distribution, which I think I did in here. I think you guys were okay with that. And then I did a video on the chapter exercises. So there's 3 videos there. Then for Chapter 8, 8 is the one that I had to skip for you guys and asked you to watch the lecture video. And there it is. There's the lecture video, and then there's the video for the exercises. So week 8 is kind of like a half week. All right, so you guys, because I did t-distributions with you, I didn't do them with Thursday, and you guys have to watch that lecture 8 video. Okay? We all clear on that? It's pretty messed up last week, so I want to make sure everybody knows what's going on. Yes, because I did not do this in class. And it's okay because it's kind of a standalone thing. Like, it's an application of still our normal distribution stuff. Okay. So I think 8's ready to go, which is good because that was last week. This week, I'm going to start something new, and I just have to double check the exercise before I turn it on. I will do that probably tomorrow, or if I can get some time today, I'll do it today. But like I said, with you guys, I was kind of a week behind because of Chapter 8, but now everything is there and ready to go. I also have activated the section of the course for the course paper. This has been the looming thing, right? The midterm was 15% of your grade. The midterm was really nothing. But the main chunk of your course grade is going to be your course paper. And I've waited as long as I could because I want to get to the part where we're actually doing the statistics that I want to see in the paper. I do not want to see means and standard deviations in the paper. What I want to see is hypothesis testing, at least using difference of means test, which is what I'm going to teach you today. So, what do we have for the paper? Well, there's a website that has lots and lots of public opinion data. So you do not have to design something and go find 20 of your friends and do all that, because we have databases that have tens of thousands of observations in them. That's the SDA website. I'll demo that more next week, but I put up a short introductory video that shows you how to pull data from there. I also have shown you how to put it into Excel. Excel is like baby steps, right? Excel is mostly just to edit files in like a column format, but I walk you through Excel and show you how to get the statistics that you need out of it. Okay, it's just, again, very simple idea with Excel. You can also use the SDA website to get the information that you need, but I wanted you to have a backup in case you just get too frustrated with the website. Okay. Also up there is a style guide. I'm a political scientist. To put up the political science style guide, I'm really not a stickler, but if I'm asking you to write a paper, I at least have to give you some information on how to format things. There's a repository for your course paper, so when it's done, you just upload it there. And then finally, I actually, when I teach the writing version companion to this class, I actually give you a Word file that says here, start here, right? It's got your title page formatted, it's got your pages formatted, it shows you these are the 4 sections of paper. It's just a way to start. Because I always laugh when somebody comes to my office to print off a paper, And I put their little flash drive in my computer. And I'm like, all right, what file is it? And then they tell me, we need to open these 3 files. It's like, no, you're doing this wrong. Like, you don't need 3 files for a paper. You don't need a title page, your paper, and then the bibliography. Like, it can all be one file. So I just went ahead and created that and put it up there. You don't have to use it. It would be smart if you did, but you don't have to. And then finally, the actual link to the data that I've talked about. So after today, you will be 100% ready to work on your course paper. Okay? There's nothing holding you back. And I will also say that the number one reason that people don't pass this class is because they don't do a good job on the course paper. I do not know how you can take a statistics class where I teach you hypothesis testing, and then you turn in a paper at the end of the class that has no hypothesis testing in it. And then you argue that we should have more guns. Like, I'm sorry, dude, but you totally deserved your D. Actually, you didn't deserve your D. I was being a gentleman and giving you your D. If any of you turn in a paper without hypothesis testing in it, you failed. I'm telling you right now, you failed the paper and probably failed the course. Or I might be a gentleman and give you a D. Depends if I like you or not. Yes. No, you don't know enough about equations. But when I say you got to put math in the paper, there has to be some computations in there, right? So if you're going to tell me, and again, this is the easiest paper in my mind to write. If you're going to tell me that men and women are different, you goddamn well better have a hypothesis test in there where you do a comparisons of means so you can tell me how different they are. Like, what was the t-score from this difference of means test? Yes. It's always best to start with the data. For you all. Like for me, no, I don't start with the data. I start with the theory and the idea. And then I go create the data. You all, you ain't got time for that. Start with the data. Right? Like I said, easiest paper in the world to write. The difference between men and women. There's tons of literature on that. Absolute tons of literature on the differences based on gender. Go to town. It's easier to do gender and race because 9 times out of 10 if you talk about race, you come off slightly racist. If it's done beforehand, sure. I will not look at it the day before it's due. But if you come to my office hours, that's what they're for. Okay. All right, let's do some math. Okay. This is the start, right? We've done all of the other things to get you in the right framework so that you can understand a little bit of the reasoning behind what we do to test a hypothesis. So I've got you hopefully comfortable with the idea of what a distribution is. Whether it's the Z distribution or the T distribution, standard normal or student's T. The idea is that our data fits a shape, and we make assumptions about our data fitting that shape. So we're going to make one little assumption today, and it is going to be the handiest thing you will learn in this class. So back in chapter 7, when Mary Kate was helping me figure out this mess, right? How the idea that we have a distribution and that distribution has a population mean, and then those and then the sample means of that population mean have their own sort of distribution. I'm going to do the exact same thing today, only this is going to be the difference of sample means. Because in chapter 7, we had one sample drawn from the population, like a classroom, right? We said, let's measure this classroom and see how our sample mean from the classroom whether or not that fits with our expectations of a population mean of all the people in the world. I'm going to do the same thing, but instead of it being one population, it's going to be two. And instead of the number of interest being what the sample mean is, it's going to be the difference between those sample means. So we're going to test the difference between two samples drawn from two populations. This curve in my hand represents all the people in the world. This side's the male side, this side's the lady side. Two populations. Okay. This represents the difference between those two populations. So X male minus X female. There we go. This is going to have its own distribution. This is going to be like that population, or excuse me, like that sample mean distribution. Only now it's the difference of two distributions. Okay? The difference. I love this example. Sometimes the book has stupid examples, and then sometimes they have these weird examples that just speak to me. And this one speaks to me because I experience it multiple times a day, mostly at daycare drop-off. Will people take longer to leave a parking space when another driver is waiting? Lucas is shaking his head like, hell yeah, I do. Make me feel pressure to get out of my parking space. Screw you. Compared to when nobody else is waiting. Now the book uses this as an intruder. So the person waiting to take your spot is an intruder. And if there is no intruder, well, that's another condition. So our population are times leaving a parking spot. One half of this distribution, or one side of the distribution, is when you have an intruder. The other side is no intruder. That it happens to include all instances of leaving a parking spot. We agree on that? Because there's either somebody waiting for you or not. So they did an observational study with 15 drivers in each condition. I knew a guy that had to do this as a job. Only he was the guy that sat side of the road and counted cars. He had a little clicker, and he's like, how many cars go over this bridge in a day? Click, click, click. Oh, Beavis. Not his given name we gave him. All right. So let's imagine someday we want to have some fun and collect some data. We sit at the window and look out to the Britton Hall parking lot. We can do that, right? And just somebody says, all right, everybody look at an area and let me know when you have a parking situation. And we can collect this data. 15 drivers in each condition. So how long does it take them to get out of their parking spot? Anybody want to guess? Like, what's our theory here? What do you think, Lucas? You think you should hurry up when somebody wants your spot? But people don't. So what would the times be? Longer for intruders or no intruders? You think it'd be longer for intruders? So we're spiteful people, right? We're like, screw you. I'm going to make you wait. Now, oh, you'd like my spot. I should hurry up. Which is what we're thinking when we are the intruder, right? What the hell's taking so damn long? Get out of the spot. Get away already. All right. So our data from this example, if you have a true intruder behind you, it took you 41 seconds to get out of your spot. With no intruder, it took you 32 seconds to get out of that spot. Right? You got an intruder behind you, you're like, I'm going to plug my phone in, I'm going to put my seatbelt on my bag so it doesn't come flying off my front seat when I brake suddenly. Happens to me a lot. All right, adjust my mirrors. Mirrors are good, okay. Seat's comfortable. All right, time to go. Oh, parking brake, got to take the parking brake off. So there's a difference in the amount of time. Now for these individual samples, the standard deviation, so the average difference from the mean, is about 10 seconds for each one. And we get a standard error, because again, we have a sample. So standard error 2.6, 2.6. So these are about similarly shaped distributions, right? Except for the mean. The mean is different. Now, if there is no effect of having an intruder behind you, what number up there should be different? Only one of them. If there is zero effect of having an intruder, what number on the screen should be different? And what should that number be? That X bar, that is the mean. Same as what? Tell me what that first number should be if you think that there's no effect. Right. If there's no effect of having an intruder behind you, the average amount of time it takes to leave the spot should be about the same, right? So we can say this a few different ways. We can say this as X bar 1 should equal X bar 2. That's saying they're the same. Another way of doing this is saying that X bar 1 minus X bar 2 should equal what if they're the same? 0. Okay. I want you to think of it this way. I'll write it like that a lot in the null hypothesis, but I want you to think of it this way. Think of it as the difference between the means now. We're drawing data from two different samples, right? From two different conditions in the world. There is a possibility that with our intruder mean, we just happen to get a sample that wasn't in the center of the curve, right? It could be out here from the tails. I mean, we only took 15 people. Maybe we took our sample in a parking lot like, I don't know, where's a lot that's hard to, well, actually, there we go. That's our intruder one. Maybe we took it in a lot like Britain, right? Where it's small, it's gated. It's not like anybody's just going to come and take our spot, right? I don't know. I'm really grasping for straws on that one. Maybe it's a small lot that's hard to get out of. You ever parked in a really small parking lot before? And like you have to do 14 different maneuvers to get out of your spot? I'm not sure how you got in it, but when you're backing out of it, you got to stop and then go forward and then back. Sometimes you just have to be okay with jumping a curb. Again, my daycare experience in the morning. Okay. So what we're going to test is not the one sample from the distribution. What we're going to be testing is the one difference from all of the possible differences. Okay? You okay with that, Doug? Looking for the difference. That's the number that we're going to test. No, I don't want to do that. So what we're asking ourselves, are these two groups different from each other? Recognizing that we only have 15 observations from a sample that is drawn from the population. So in chapter 7, when I first introduced this insanity, I basically said we're comparing our sample to the population, and how likely is it that we get this sample from the population. Now what we're saying is, how likely is it that we're going to get this difference between the two samples, the difference between the intruders and the non-intruders times, from a population of Parkers. Right? So we're looking at the difference between the two sample means. This is the sampling distribution of the difference. So that's the reason why I made it x1 minus x2, because it's a distribution of all possible differences. Again, we're just labeling this extra curve something different. That's all we're doing. We're just changing the name because we have our one number, but we got that number by taking the differences. It's still the same concept. It's still the idea of you took a sample from a large population, and because it's a sample, things happen. You might not get the right one, right? You might get a strange number. And so we have to basically recognize that your sample is in and of itself a distribution. With this new distribution, we can just use the same methods that we've already developed around our standard normal and around our student's t. But now we just have to incorporate the fact that we're drawing two samples. So I'm going to warn you, the math might look a little difficult, but it's not, because it's still just subtraction and addition. And it's still the same four functions. It's just that it gets longer. And the problem with longer math is it's more opportunities to make a stupid mistake. Not that it's any harder, it's just more work. Okay. The other thing about this is that our notation is going to start telling us that it's not just a sample, it's actually a sample of differences. So our subscripts are going to look like there's math in them, but it's not. It's just to show that we're dealing with the difference between two groups. This new distribution that we're using, we call it the distribution of the difference. It is just like a normal, or approximates a normal. So the mean is centered on 0, which is great because we usually assume that there are no differences. It is approximately normal, which means when it's not normal, we can use student's t. The shape's determined by the sample size. That's student's t. And it also has a variability. And because we're dealing with samples, we use standard errors. So again, notation is just slightly different, but it's in the same vein. No new letters. First step in any analysis, what's the null hypothesis? The null hypothesis always says that there's no relationship. So the average time for when you have an intruder should be the same as when you don't have an intruder. So the nulls have these two means being equal. You'll notice that they're using population figures here. Why? The samples are taken from the population, but what are we trying to do as social scientists? Yeah, we're trying to make inferences about the population from our samples. So it makes sense that our null hypothesis talks about populations, because that's what we're trying to infer. That's what we're trying to test. The alternative hypothesis, this is an easy one. There's a difference. They're not equal. If we wanted to go directional, and we have a specific theory of human behavior that we're trying to test, we could, let's see, that's less than and that's greater than. So what kind of theory would it be that the intruder time is less than the no intruder time? What are you saying about human behavior? That we're nice and considerate of others, right? Oh, geez, there's somebody behind me. I better skedaddle. Shove that thing in reverse. I'll put on my seatbelt later. Let's get them in this parking spot so they can get where they need to go. The alternative is, yeah. Oh, you want my spot? Better check my lipstick. I don't even wear lipstick, but I'm checking it. This is my spot. Actually, I do have a spot. It's the first spot that you can park in on this side of the building. That's my spot. All right? I'm not giving it up. It's my spot. I might not have a sign on it, but, you know, metaphorically, I dog peed on it. That's my spot. Don't park in my spot. And if you want my spot, you're going to have to wait a little while, because it's mine, and I'm going to enjoy it. Make a decision about the null hypothesis? Well, how are we going to do that? Well, we need to figure out, given our sample, what have we observed? How probable is it that we have observed from our sample what we have observed, given what we think the distribution is shaped like? So here's some steps. First step, calculate degrees of freedom. Okay, so let's think about this for a second. How many observations did we have? 15 of what? Each. How many observations did we have? 30. Because we had 15 with no intruders and 15 with intruders. Okay? So our N we actually have two N's because we have two groups. N of the first group and N of the second group. Degrees of freedom is usually N minus 1, right? Well, what do we do now? Well, there was some reason we subtracted 1 from a sample, but now we have 2 samples. So it's probably going to be N1 minus 1 and N2 minus 1. That makes sense, right? Because we really have 2 samples. The reason I do this is because I want you to start thinking about, okay, we did it last time like this, but now this is just slightly different. How would we do the same thing? We'll get to that in a second. Set alpha. All right, with alpha, does it matter that we have 2 samples with alpha? Because what is alpha really? Yeah, it's the 0.05. 0.05. Because 0.5 is half, right? 0.05. I do that all the time, Gregory. That's our decision rule. So basically we're saying, listen, we want to have 95% confidence or 95% likelihood in our outcome. We're okay with just about 5% error. Identify the critical values and state a decision rule. Okay, here's the thing. Identify the critical values. If it's lots of observations, what's probably our critical value? Remember, bucket on the floor, I draw the distribution, and I'm going to shade a region. What magic number am I looking for if I have a ton of observations? 1.96. But let's say I don't have a ton of observations. What do I have to use instead? I have to use that t-table thingy. All right. So that just, again, depending upon our sample size, it depends on which test we're going to use. All right, so let's go through this. First, calculate degrees of freedom. Our inclination was correct. So degrees of freedom for multiple groups, like a difference, n1 minus 1 plus n2 minus 1. Because for each sample, we have calculated characteristics of that sample, like the sample mean. That burns an observation up. So our degrees of freedom is 28. We good with that? Pausing for the slide copiers. Set alpha, identify the critical values, and state the decision rule. Okay, alpha, 95% likelihood, so it's going to be 0.05. We're going to use a two-tailed test. We had competing theories, right? We had two alternatives as to whether you should be faster or slower coming out of that parking spot. I'm okay with doing a two-tailed test. 28 degrees of freedom. If you look that up on the t-table, it's t for 0.025 in one tail, which we're using two tails. That's why I did 0.025 in my middle column. I hope it's 2.048. I'm out of t-tables. Does anybody have one they can look up and double check on me? Is that the right number, Lucas? Middle column, 28 degrees of freedom? 2.048. Okay. So now when I draw my little picture is going to have my curve. I'm going to shade the 5% in the two tails, and I'm going to write down where my value of t is on the border. All right, those are the cut points. The what do they call them? Critical values. So if I get a positive greater than 2.048, I can reject the null hypothesis. If I get a negative greater than, or I guess less than, negative 2.048, reject the null hypothesis. That is saying, remember, that the difference that we observe, because this test is centered on the idea that mu1 minus mu2 is 0. Centered on 0, that there is no difference. And we want to see how far out our sample is from that expectation. That's what we're doing. So let's figure it out. Here is the equation. Our t is the difference between the two groups. Where's mu? Mu's there. Where is our expectation? Because didn't before, when we were doing these tests, we had sample minus population? Where'd my population go? It's not there. Why isn't it there? Every other thing was x bar minus mu. Where's the mu's? Why isn't the mu's up there? Fine, I'll put it in. Where'd the mu's go? So what should the mu's equal? 0, right? So I don't need to put that up there. I could put that up there and confuse the hell out of you and be like, oh no, more things. But I don't. Why? Because our expectation, remember, we're testing a null hypothesis framework, that there is no difference. So we expect mu1 minus mu2 to equal what? 0. So we don't even need to put it in the equation. It's just gone. Because whatever you have minus 0, it's what you have. Okay? So if we're going to do this, t, the top is easy. All right, we have our two sample means. 41 minus 31, right? This is where I ask for patience. I'll just show you. It looks bad. It's not that bad. Because, remember, what we have here with our subscripts, we have the standard error of the difference. Remember, that's the name of our second curve that we put on top, right? It's a difference curve. So we have to compute the standard error from the difference. And so what we do is we take into account each one. So if this were just asking for the standard error of x1, it would just look like that, right? It would be the square root of, right? That's just what it would look like. But now we've got 2. So it's 2 parts. The other thing I want to throw in there is now we got squares too. Sorry about that. Got to have squares in there. Why? Because we're adding two things together and we need to deal with the negatives. The potential for negatives. So yeah, we're squaring it, but we're taking the square root of it. We have to guarantee that this number is positive. So it's a little, additional steps with the math, but nothing you can't handle. Nothing that should cause cold sweats. Your calculators can handle it. These are just subscripts. These aren't even really that important. But it tells us which group to use. Okay. So we do the math, take our time, don't let it scare us. It looks like a regular t. You got a subtraction at the top. You had to do a little something to get the denominator. Divide it out. T equals 2.42. So this is telling us how far away from that expectation of 0 our sample difference is. The expectation is 0 seconds. We observed about 11 seconds difference. How far out is that? .42 puts us way out here. This is in our rejection zone. So what can we decide about the null hypothesis? We reject it. There's something going on in behavior when you have intruders. That's what our sample is telling us. Now we've crossed that 95% threshold. The book really likes you to go out and well, what about 0.01%? What about that 99%? Yeah, don't worry about that. Okay? For us in the social sciences, this is the bar. So when we, as social scientists, in journal articles report these scores, we like to show you that it is significant, statistically significantly different in this case. So what we do in our tables is we put a little star next to it, saying, look here, shiny. All right? This is important. What we've also taken to doing is putting more stars out here. Right? So 1 star is alpha equals 0.05. 2 stars, it equals 0.01. And 3 stars, 0.001. Like, bam! Listen, kids, it doesn't work that way. All right? Every time I see this, I'm like, oh. In fact, we have a name for people that do this. Call it stargazing. Right? Oh, it's not just different, it's super duper significantly different. Listen, it's not like we're killing the null hypothesis here. Like, you know, levels of extremity. Like, this is rejection, this is death, and this is drawing, quartering it, and posting it at the 4 corners of the kingdom so that no null hypothesis shall ever get the idea of being like that again. It's like, listen, dude, I got it. You put the star there. I looked. That's cool. This is overkill. Right? This is wearing like letters on your chest, your hat, and showing off your tattoo. Like, listen, tone it down. Right? This is enough. There's no such thing as super significance. It's like a light switch. It either is or it isn't. So that's why when the book says, well, you have 0.01, like, listen, I already rejected the null hypothesis. I don't care how much I get to reject it, it's gone. It's rejected. It's not happening. Right? There's no need to make it feel any worse. But if you wanted to, right? If you want to be a stargazer and just plow those stars in there, go right ahead. I don't care. It's like the professional norm to do it. But to a statistician who actually understands what you're trying to do, the difference between rejecting the null at 0.05 and 0.000000001, you can put 15 stars on there or some other symbol. Have fun. I know how the math works. I also love it when people say, well, it was almost significant. It's like, no, it doesn't work that way. You're not almost pregnant. Either you're pregnant or you're not. You're also not ever super pregnant. Right? I'm 0.001 pregnant. No, you're not. We can reject the null hypothesis that you're not pregnant, but you're still just pregnant. Right? And you're never almost pregnant. Like, that's not a thing. You're just fat. I'm almost pregnant. No. Doesn't work that way. Right? This is a decision point. You're either on one side of it or the other. Well, it's 1.954. Sorry, still not 1.96. You don't get to cross that threshold. All right. The mean departure time for the 15 drivers in the intruder group is significantly greater. So that word significantly is not relative to the time. Because is 11 seconds significant in any form or fashion? I mean, I can waste 11 seconds like nobody's business. Nope, 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 nope. I can just keep doing that for 11 seconds. 11 seconds is not a significant amount of time. That's not what that means. What it means is that the difference or what we have observed, is statistically significantly greater. That word should always be in there, because otherwise it seems like you're making a value judgment. And people who don't know statistics don't understand what we're saying when we're saying significant. Significant in a statistical sense just means you got to reject the null hypothesis. That's all it means. That's why you shouldn't also put qualifiers in there. Well, it's approaching significance. No, it's either significant statistically or it's not. You don't approach significance. You're not significant adjacent. You're not significant-ish. Right? You are either statistically significantly different in this example, or you're not. And again, people in the field, when they do this, that's a sign that they don't know what they're talking about. Because the statisticians in the room, again, you're either pregnant or you're not. You're not leaning towards it. Then the mean departure time for the 15 drivers in the no intruder group. You can't just say, this is my result. You have to say, this is my result relative to what we already kind of thought we knew about it. The present series of studies is consistent with prior findings, so we meet the expectations, that people display territorial defense in public territories. What is new about the present research is that it suggests people sometimes display territorial behavior merely to keep others from possessing the space even when it no longer has any value to them. So think of other situations in which people display territorial defense. Okay, so seating in a theater. How do you defend your territory in a theater? Yeah, how do you spread out though? Like, yeah, you put my coat, like, I'm not going to sit on my coat. I'm going to put my coat in the 2 seats next to me. So you can't sit in those 2 seats next to me. Okay. How else do we display territorial defense? Not just in parking, but think about it. Think about our lives and all the various situations that we can do this. How do you do it at home? Okay. What else do you do at home? You lock your doors. That's a form of territorial defense, I guess. Here's what we've done at our house. Theoretically, I have a neighbor who doesn't keep very good care of his lawn. So I just took it over. So how do you take over somebody's lawn? I mow it. I plant flowers on it. When his things get overgrown, maybe, perhaps, I cut them down. That's territorial defense. Right? So the little shared island that we have in the front yard, yeah, it just looks like how I want it to look like. And that bush on the side of their house, that it's a lot smaller than it used to be. There's another way to do territorial defense. And the guy who owned the house before us put in a fence that was bigger than his lot. He didn't just defend his territory. He was taking some of mine. Now, you know me. What would happen to that fence? It wouldn't be there anymore. Okay? So we do this in our daily lives. And sometimes it's not polite. like when you're sitting someplace, gentlemen, and what do? You sit with your legs as wide open as humanly possible. Man spreading. It's a thing. All right. But we not only do this in our daily lives, but we do it in situations where it's temporary. When we have a changeover in classes, I'll wait 5 minutes. You got 5 minutes to pack up your stuff and go. But you hit that 5th minute, what's going to happen? I need my territory. I'm going to come in, and so I did this last class. There was a professor here, still had their stuff around. I just came in and put my stuff down because I needed to have some territorial defense. Like, I got to get you out of here so I can set up my computer for the next time. Even though this space to me is temporary, right? I only use it the days I have to. Like, I hate this room. I don't want to be in here. Like, I didn't put my name on the door or anything. This is just for this semester. But my time is my territory. When we do this, we're making an assumption. And sometimes we can break that assumption. With the last example, it just so happened that those two different distributions were similarly shaped, right? They're centered about the same mean, they had the same spread. But there are times when there's difference in the variance of the two groups. So let's say this is our intruder group and this is our no intruder group. We make an assumption that the variance is the same. It's known as homogeneity. Homogeneity of variance. The assumption that the variance is the same. But what if in fact it's different? We sort of correct from this when we compute that joint standard error. So we don't have to worry about it too much. As long as it's a small difference, we'll be okay. So was our difference small? Let's go back to our original data. Was our difference small? Is that from 2.69 to 2.60? Is that a small difference? Yeah, we're okay. If this were 200, then we might have a problem. All right. It also was nice that in this instance, the sample size was the same. We could have situations where we don't have equal sample sizes. We can adjust for that. So here's another example. Can kindergartners and first grade students jump rope for 30 seconds? If we have a healthy living and exercise intervention, should that make them more able to do this? We love experimenting on kids. We really do. We do it all the time. Like, a lot. We really do. We don't do this with adults, right? Once you're an adult and you're in college, nobody cares if you come to class. Nobody cares what you eat or if you get exercise or not. But man, my kid, she has like the most rigid schedule as a second grader. Like, oh, it's Tuesday. It's art day. She will get art in her life. All right. John's not even in school yet, and somehow we're in a reading program at pre-K. Then we got lists of books to read. Like, these are just experiments we're performing on our children. It really is. So let's see. Some program, let's have a group where, I don't know, maybe they train or we give them apples instead of Pop-Tarts for snack. Also a true thing. My schools, my daycare used to give my kid Pop-Tarts as a snack. Used to. They changed that. So we've got two groups. The ones that were in the intervention group, so the ones that have been treated. There's 16 of them in that group, and there's 11 in the control group. The group that just has nothing. Like, we don't care about you, kid. Let's just see what you do with this rope. An actual study. The intervention group, I should have read that a little bit more closely. Is this the time? Let's say it's time in terms of seconds. Like, how long can you jump rope for? Yes, let's just say that. I'm guessing. That's probably correct. Actually, it's actually wrong. It's the number of jumps in 30 seconds. I'm more like the control group. Like, I lay the rope down and then I jump over it, and then I pick the rope back up, and then I jump over it again. That's more my jump roping style, especially to get this weight up in the air that many times. All right, so the intervention group, clearly they got more jumps in the 30 seconds. Average was 27. Group 2, they got, let's say, 12 jumps in. Those kids need to practice some more. It's the control group. All right. About the same in terms of our variance, right? 10, almost 10. We're okay there, but that's all right. Again, t-distribution can handle a little bit of difference in the variance. Talk about the null and alternative hypothesis. Again, we're comparing two groups. Are the groups the same? Or are they different? Null hypothesis says the intervention shouldn't matter. It's jump roping. Like, really? Do you need an intervention to learn how to jump rope? Absolutely. Versus an alternative hypothesis that says, well, actually there should be a difference. And again, two-tail test, we're not going to focus too much on it. Degrees of freedom, we just did this, no change here. Number in your group, -1, plus the number in the second group, -1. That's still the same. So we have 16 in one group and 11 in the other group. That's a total of 27. 27 minus two groups is 25. Set alpha. Alpha is going to be the same, 0.05. Identify the critical values. So hopefully you got a decent table that has 25 on it. That critical value is 2.060. So when we draw our curve, because remember, bucket on the floor, you always draw the curve, our shaded areas are going to start at both positive and negative 2.060. Got to calculate T. Looks the same, right? The difference between the two groups. How much of a difference was there? We can ignore the difference between the two populations because they cancel each other out and they're zero. And we have to compute a standard error of our two groups. So this is exactly the same. This is where it goes a little different. Sorry, I didn't create this. Again, it's all math you can do, and no stats professor in a million years would ever expect you to memorize this equation. But because the two groups are different sizes, we gotta put that in pretty much everywhere. So, just looking at this, remember PEMDAS, parentheses first, so the first thing we do is anything in a parentheses. Start from left to right. So the first thing in a parentheses, n minus 1. Got that. That'll be 16 minus 1. Any more parentheses? Going across, N2 minus 1. That's going to be the 11 minus 1. I got that. Scanning across this thing. Well, this isn't that bad. All right? I'm just adding two fractions together. 1 over n plus 1 plus 1 over n2. All right? So that's just our two sample sizes. I can do that. See, that doesn't look that bad. All right, that's through. Parentheses first. Next, exponents. We actually have exponents in here. We have these squares. Remember I said we have to make sure this is positive. So there's two squares in there. The square of sample 1 standard deviation and the square of sample 2 standard deviation. These subscripts could be a little smaller, but again, I want to make sure you can read it, so that's why you have to remember that each individual letter can have both a superscript and a subscript. The superscript here is the square, the subscript is the 2, the group number. Multiplication. I do have some multiplication. I have multiplication right here, where I have to take these two groups and multiply them together. So I'm going to multiply, hopefully I'll do my exponent, and then I'll multiply these two, the 16 minus 1 and the 10.18 squared, which should be a different number by now. And then I've got my 9.74 squared times 11 minus 1. So I'll go through and I'll do that. And then once I have that, I can add them together, do the division, and then I got to multiply that thing by this fraction that's sitting over here. Quite honestly, this is why I like the $100 calculator. Because I can sit and just type this whole thing in the $100 calculator and hit enter. Yep. See, I just like doing it that way. The other reason is if you keep doing these things piece by piece, you're going to introduce rounding error. Because let's look at all the things that you're going to end up rounding. You're going to round this square. You're going to round it again when you multiply it. You're going to round this square. You're going to, again, round it when you multiply it. This number you're going to round, and this number you're going to round. And then you're going to round that times, you're just going to do a ton of rounding. And all that rounding, sad to say, adds up. So, if you already own the $100 calculator that you were forced to buy in high school, this is actually a good reason to break it out. Or, just be really careful if you do it by hand. Go out more than 2 digits in your decimal point. Because we're making a big decision here, right? We're rejecting a null hypothesis or not based upon part of this number. So sometimes it's best to do the extra work. And it goes on for slides. All right, 3.88 is what you end up with. Is that what you got? That's the other problem. You got to be careful when you do this stuff. Is it close to that? I think you used the wrong function. Okay. Yeah, you should end up with a single number. All right, so this is not our t-value. This is just the value of what's going to go in that denominator. All of that work just for the denominator. But we needed this standard error. So all that work, 3.88, gives us a t-value of 3.97. What are we going to do? Sure. I think there's some rounding in there. The other thing, too, is what was on the slide probably needed extra sets of parentheses, particularly around the exponents. So you have to use extra parentheses when you use your calculator. Yep. Sure. That's this. That's just, S of group 1, so that S means standard deviation, right? That's our measure of variance for our sample. That's chapter 4. Right? That's nothing new. I'm not springing anything on you. The only thing that I did different is we have a subscript now because we have 2 groups. We have group 1 that have gotten the treatment and group 2 that didn't get the treatment. Yep. Yep. That's all it is. All right. So, again, bucket on the floor, you draw your curve, 3.97 as a value of t. We're way out here in the tails, but it doesn't matter. We're going to reject the null hypothesis. What does that mean? If you want kids to be better at jumping rope, train them on how to jump rope, or make them healthier or more athletic or whatever. The average number of rope jumps in 30 seconds is significantly greater for the 16 students who received the intervention than for the 11 students in the control group who did not receive the intervention. This finding suggests that programs emphasizing the enhancement of basic motor skills, like jumping, that children apply in a variety of games and sports may be an effective approach to increasing overall activity and fitness levels of young children. I'm going to call a big question mark on the second half of that, but they do get better. So if they have physical activity as part of school, they are better at physical activities. I'm actually going to stop there. But I just want to make sure that we're all sort of comfortable with what the idea we have learned today is. So we've got a new distribution. That distribution is the distribution of differences. Let's just call it that. Differences of means. Could be something else, but let's just say the distribution of differences. The null hypothesis says that we have no difference between groups, whether it's kids who get a treatment, whether it's you have a parking stalker behind you, whether it's you're a man or a woman, whatever. You have the idea of 2 groups. Are the groups different given what we have observed? We collect a sample. We note the characteristics of that sample by computing a measure of central tendency called the mean and a measure of variability, the standard deviation. We then use inferential statistics. If it's small, we use the t-score. If it's bigger, the t-score turns into the z-score. We test the hypothesis of that there is no relationship by finding out where our sample is relative to the population. And if the assumption is that the population differences are 0, we put that in the center of our curve, and we go out however far the t or z score tells us we are from that 0 to decide if we're going to reject the null hypothesis that our observed sample, in this case an observed difference in our sample, how likely it is that you would observe that when in the real world you shouldn't see any difference. That's what we did today. All we've done is sort of insert the word difference in what we have done in chapter 7 especially. There's one more type of doing this, differences, and that's when you have the same subjects. We don't use this a lot in political science. This tends to be more in public health. I'm going to put this in the supplementary video. And this is when you have differences between the same sample, the same people, from a pre-test to a post-test. The math is a little different. But I'm going to put this in a video. And the reason I'm going to do this is because, and not do it here, is because when you guys start thinking about writing your paper, you're going to go to the SDA website and you're going to look at the public opinion polls. What you'll do is you'll look at some of the questions. The example I use, I think, in the videos is spanking children. I've got children. I'm tempted to spank them a lot, but my wife has decided that we don't do that, so we don't spank our kids. There's a question in the survey about, hey, should you spank your kids? And the example that I use is, I wonder if there's a gender difference between views on spanking. I wonder if men are more likely to spank their children or say that you should spank your children, and women are less likely. And so that's the example that I use. I have two groups, but it's not a repeated sample. It's not a pre-test, post-test design. So that's why I don't really get into that. There are some questions in the national election study that are pre-test, post-test, like we talk to you before the election and then we talk to you after the election. But quite frankly, none of you are going to use that setup. A lot of you are going to go, I want to do a difference in means test for this paper. And that's why I'm going to stop here on this and put it in a video. Any questions? All right. I'll also, tomorrow, go ahead and do the sample exercises from the chapter so you can see, again, the process of going through and doing this.